Welcome back to AI.Code.Cast. Ready for another deep dive?
Absolutely. Always excited to tackle a new challenge.
Today, we're going to be looking at a classic, the running sum of a 1D array. Sounds simple enough, right?
It does. But, like many things in coding, there's more to it than meets the eye.
Exactly. Like, how can we make it really efficient? That's always the goal, isn't it?
For sure. Who wants slow code?
No one. So before we get into the fancy stuff, let's start with the basics. What exactly is running sum?
Okay, imagine you have an array, just a list of numbers. The running sum at each position is the sum of all the numbers up to that point.
Okay, I think I did that. So if we had, say, 1, 2, 3, 4.
Right, so the running sum at the first position is just 1. Then at the second position, it's 1 plus 2, which is 3.
And then 6, and then 10. Got it.
Perfect. Now, the most straightforward way to calculate this is what we call the brute force method.
Brute force, huh? Sounds kind of,
Well,
forceful.
Well, it is in a way. You basically loop through the array, and for each element, you add up all the previous ones, plus itself.
So lots of adding going on.
Yep. And that's where the inefficiency comes in, especially with larger arrays. You end up doing a lot of the same calculations over and over again.
Ah, I see. So it works, but it could be better.
Precisely. There are more elegant ways to approach this that avoid all that repetition.
Elegant. That sounds more like it. So how do we get to this more sophisticated solution? What's the key insight we need?
Well, think about how each running sum builds on the previous one. Maybe there's a way to use that to our advantage.
Yeah. Instead of starting from scratch each time, we could maybe store the sums we've already calculated.
Now you're thinking. That's the spark that leads us to more efficient approaches, which we'll explore in the next part of our deep dive.
Back again with AI.Code.Cast. Still diving deep into running sums.
Yep. We started with brute force, which wasn't the most elegant.
Definitely room for improvement. You hinted at something better, though, right?
Exactly. Remember how we talked about using the previous sums?
Yeah, like building on what we've already done.
That's the idea behind the prefix sum approach.
Yeah.
Basically, we pre-calculate all the sums up to each point.
Pre-calculate. So we do a bunch of work up front.
Kind of. It's like preparing all the ingredients before you start cooking.
Okay, I like that analogy.
Yeah.
So how does it actually work?
All right, let's say we have our example array again. 1, 2, 3, 4.
Our trusty example.
We create a new array to store the prefix sums. The first element is easy. It's just 1.
Right, because the sum up to the first element is just itself.
Exactly. Then, for the second element, we add the first 2 elements of the original array. 1 plus 2, which gives us 3.
So the prefix sum array is like a running total as we go along.
You got it. And we keep going like that. The third element would be 1 plus 2 plus 3, which is 6.
And the fourth would be 10, right? Because 1 plus 2 plus 3 plus 4.
See? You're getting it. So now we have this prefix sum array, 1, 3, 6, 10.
Cool. But how do we actually UEC this to get the running sums we originally wanted?
That's the best part. It becomes super simple. Let's say you want the running sum up to the third element. You just look at the third element in our prefix sum array, which is 6. Boom. That's your answer.
Whoa. No more adding everything up again and again.
Nope. Each prefix sum has already done all that work for us.
This is way more efficient than brute force, right?
Absolutely. We've brought the time complexity down to ON.
ON. That's linear time, right? So it scales nicely even with big arrays.
Exactly. Much better than the ON2 of brute force.
Okay, I'm sold on the speed. But
Yeah.
didn't we create an extra array to store these prefix sums? Doesn't that take up more memory?
You're sharp. You're right. The space complexity is also, there's always a trade-off, isn't there?
Seems like it. Faster calculations, but we use more memory. It makes me wonder, though, is there a way to get the best of both worlds?
Now you're asking the really interesting questions. And the answer is maybe. There's a technique that lets us do this in place, meaning we modify the original array directly.
In place. But wouldn't we overwrite values we need later? How could that possibly work?
It's pretty clever, actually. We'll unravel that mystery in the final part of our deep dive.
And we're back. It's AI.Code.Cast, the final part of our running sum saga.
The climax, where we reveal the ultimate technique, the in-place solution.
Yeah, this is the one I've been waiting for. It sounds kind of magical, like we're bending the rules of coding.
It's definitely clever. Remember how we talked about modifying the original array directly?
Yeah, but I still don't get how we avoid overwriting important values.
Okay, let's break it down. We're going to go through the array step by step, updating each element as we go.
Okay, got my mental whiteboard ready.
Good. So let's take our example array 1, 2, 3, 4 one last time.
Our old friend.
The first element is easy, right? The running sum up to the first element is just itself, 1.
Right, so nothing changes there.
Now, for the second element, we add the first element to it, so 1 plus 2, which gives us 3. Our array now looks like 1, 3, 3, 4.
Wait, hold on. We overwrote the 2 with a 3. Isn't that a problem?
Not at all. Because the 2 has already done its job, it's been incorporated into the 3, which represents the running sum up to that point.
Oh, I think I see. So we're not just adding up the original numbers, we're building on the running sums as we calculate them.
Exactly. So moving on to the third element, we take the updated second element, which is now 3, and add it to the third element, which was originally 3.
So that gives us 6, and the array is now 1, 3, 6, 4.
Perfect.
Yeah.
You're getting it. Now for the final element, we take the updated third element, 6, and add it to the fourth element, 4, giving us 10.
And we end up with 1, 3, 6, 10, our running sum array, but we never created a new array.
That's the beauty of in-place modification.
Okay, I gotta admit, that's pretty slick. So what's the efficiency like?
We still have the ON time complexity, meaning we only loop through the array once.
Same as the prefix sum approach. But what about space?
This is where it gets really good. The space complexity is O1.
O1, constant space.
Yep. No matter how big our original array is, we're not using any extra memory to store the running sums.
So we've got the speed of prefix sums, but without the extra memory usage. Amazing. Is there any downside to this?
Well, the trade-off here is that we modify the original array. So if you needed that original data later,
You'd be out of luck. Got it. So each approach has its strengths and weaknesses.
absolutely. That's why understanding different algorithms and their trade-offs is so important.
This has been a fascinating deep dive. We started with brute force, explored prefix sums, and ended up with this super efficient in-place solution. It's incredible how much depth there is to even a seemingly simple problem.
And that's what makes coding so fun. There's always something new to learn and explore.
Couldn't agree more. Thanks for joining us on AI.Code.Cast. Until next time, happy coding.